An object moves through the dark. What must we measure to describe its motion, and what must we know to explain why that motion changes? We can already see 4 clues: a place, a sequence of moments, the object's resistance to change, and an interaction acting on it. Classical mechanics begins with that question. Space, time, mass, and force will become a connected language of motion. Strip the laboratory away. We will rebuild that language from the measurements themselves, one observation at a time. Begin with one object, floating in an otherwise empty region. We can see it, but the question where has no numerical answer yet. To measure a location, we first choose a reference point. Call it the origin, O. From that origin, let 3 perpendicular directions grow, x, y, and z. Extend their markings into a coordinate grid. The grid is not painted onto nature. It is a measuring scaffold that we chose, so positions can be stated precisely. At our first observation, the object is here, at point A. Grow an arrow from the origin to A. This arrow is the first position vector, r1. Notice what it describes, where A is relative to our chosen origin. Now watch the object itself. It leaves A. Follow it as it bends through space, passing above the grid and curving toward a new location. The glowing trail records the route actually traveled. Finally, it slows and arrives at B. Throughout the journey, keep a faint copy at A. That memory matters. Without both the starting and finishing positions, we cannot describe the change. Only now are we ready to draw displacement. Place its tail at A, the starting point. Let the arrow grow directly to B, the finishing point. Displacement ignores the curved route. It records only the change in position, delta r equals r2 minus r1. But a start and finish still do not tell us how the motion unfolded. Reset the object to A and add a clock. Each pulse of this clock marks the same duration. At the first pulse, record the object's position. Now let the clock continue. At T1, record the next position. Wait for the same duration. At T2, record again. The clock repeats the process at T3 and then at T4. Every gap in time is equal. Watch the spatial gaps. They become larger, so the object covers more distance during each equal interval. Its speed is increasing. Let us reorganize those same observations, not invent new ones. Rotate our view. The horizontal direction will represent time. The vertical direction will represent position along the track. Now move each recorded observation to its matching pair, its time and its position. After the points have arrived, join them. Choose 2 observations. The rise is the change in position, and the run is the change in time. Their ratio, delta x over delta t, is the average velocity during that interval. Bring the 2 observations closer together. The secant line settles into the tangent at one instant, whose slope gives instantaneous velocity. Here the graph becomes progressively steeper. The velocity is changing with time. That change of velocity is acceleration. But that description leaves a new question. What makes the change happen? Reset the laboratory. Let one amber capsule glide along a nearly frictionless track and bring a cyan pusher toward it. The pusher touches the capsule, compresses slightly, and the capsule's velocity begins to change. While they remain in contact, pusher and capsule interact. A force is a push or pull exerted on an object by something else. Contact is one possibility. A field can also exert force without touching. Represent this force with an arrow attached to the capsule. Its direction shows which way the push acts. Its length represents magnitude, how strong the push is. Move the pusher to the other side and the arrow reverses. Increase the push and the arrow grows. Force is a vector. Now let the interaction end. The pusher retracts and the force arrow shrinks all the way to 0, but the capsule does not stop. On this nearly frictionless track, equal clock pulses find it at equally spaced positions. It keeps moving with constant velocity. The push changed its velocity. It does not need to remain for motion to continue. Next, place two equal-sized capsules on parallel tracks. Their appearance does not reveal their masses. We will compare mass through an experiment. Apply the same controlled force for the same duration, then observe how strongly each motion changes. Two identical pusher pulses grow together. At equal clock intervals, the first capsule gains velocity quickly, while the second gains it slowly. The same force produces more acceleration in the smaller mass and less acceleration in the larger mass. Only after motion reveals the difference do we label them 1 kilogram and 4 kilograms. The larger mass resists the change in velocity more strongly. This resistance to a change in motion is inertia. Mass measures inertia. A massive object can certainly accelerate. Producing the same acceleration simply requires a larger net force. Watch the heavier capsule repeat the first response only when its force grows fourfold. Now keep mass fixed and change only force. Reset two recordings of one identical capsule. Give the first a gentle push and the second a push 3 times as large. The longer force arrow produces the larger acceleration. With mass unchanged, acceleration grows in direct proportion to net force. Real objects often experience several forces at once. Start one capsule moving, then let two field emitters pull from opposite sides with equal strength. Both forces remain present, but their vector sum is 0. The net force is 0, so acceleration is 0. The capsule need not be at rest. It continues with constant velocity. Now make the rightward pull larger while the capsule initially moves left. The equal parts of the opposing arrows cancel, leaving a net force to the right. For a moment the capsule still moves left, but it accelerates right. It slows, stops, and reverses. Acceleration points along the net force, not necessarily along velocity. The controlled comparisons now fit together. Keeping mass fixed, greater net force produced greater acceleration. Holding net force fixed, greater mass produced smaller acceleration. Let the physical evidence assemble the relationship. Net force equals mass times acceleration. F net equals ma. This is the structure Newton's second law will formalize. One final distinction prevents a common confusion. Keep the same capsule, but weaken the surrounding gravitational field. Its mass marker remains unchanged. Its downward weight arrow becomes shorter because weight is the gravitational force acting on it. Mass measures inertia, weight is a force. We can now read the experiment as one connected chain. Position and time describe the state of motion. Mass and net force tell us how that state responds. Together, they turn observations into a prediction. Classical mechanics now asks a forward-looking question. What happens next? Newton's laws will supply the rules. But every position, velocity, and acceleration we recorded was measured on a chosen grid from one viewpoint. If another observer carries a grid that moves, turns, or accelerates, what changes? In the next video, reference frames will answer that question and prepare us to state Newton's laws precisely.